back down, and then bromide would leave, and you would have something that looks like this, right? OH and then plus Br minus. Yep, this all looks familiar. Okay, so what were the three big rules that I told you that we need to know for biochemistry mechanisms? What are the three rules? Get it in the chat section. Three rules. Rule number one is oh good, I'm seeing them coming out. Cause resonance, that's number three. No Texas carbon. That's not an official rule, but you should definitely live by it. Yes, beta decarbonyl is labile, and the very first one is acid base are quick, right? So acid base. So because of that, and because everything's happening in water, you can actually simplify reactions. So let's take a view of this same.
It was recording.
Oh, weird. Okay. So you have a couple of protons right here that were working, and so these guys here also can be abstracted, right? And the reason for that is because those protons can resonate like that. Does that make sense? See, this is alpha beta decarbonyl. Make sense in the chat? Yep. So water is usually a leaving group, is what Robin is saying. Yeah, frequently water can be a leaving group for many kinds of reactions, but in this particular instance, that wouldn't be what we would see. Okay, so let's move along here to some of the examples that I gave you, some of the real world examples. Let's take a few of these and work through a couple of these, yeah? Is this working for people? Is this helpful, by the way? So we had three rules that we covered. We got a couple of thumbs up. Looks like people are, yes, good, super helpful, good. I'm happy to post more of these if you guys find these useful, and we have live chats every, 3 times a week. So if you want to see more of this stuff, we can cover other stuff, and we'll just put out a poll. So if you want more of this material, we can. Okay, so now let's work through some of the examples. So I posted these all in D2L. You guys can work through these. I'll also post out the answers so that you guys can work through them on your own. But I think it's useful to work through the examples before you look at the answers, because we're not trying to memorize them. We're trying to learn the rules. So okay, this is a great example of a nucleophilic substitution reaction that's happening in biochemistry. So SN2 is super common, and what happens is this hydroxyl is going to attack that phosphate, okay, and this is going to leave as a leaving group here. Well, I guess it's going to go through this, Carly has prepped this to show you the intermediate form right here that looks like this guy here, or we can simplify it all the way out to have ADP leaving and showing this glucose 6-phosphate form down here. But if we want to show each of the steps, then we would have a base abstract the proton that would go to here, and then wait a minute, why is she doing that? That's not right. You would have this happening. There we go, and that looks more likely. Yeah. Yeah. And then you have ADP as your leaving group and your phosphate. So that's a really common sort of intermediate reaction. You can actually simplify that reaction mechanism just ignoring this intermediate here altogether if you'd like, and you would do that just by drawing this guy as an addition right up front. You could do that as having these things resonate up and back, and then having this go out to a proton. So that's the one-step version of it that takes you from this step right here all the way to this step right here. Does that make sense? This is how we simplify things in the biochemistry. Anyway, but the neat thing about this is that we have a one-step nucleophilic, or we have this additional elimination reaction that's happening here, and we have the replacement of the loss of an ADP, which is a typical kind of mechanism. Does that make sense to everybody? We do another example here. Oh yeah, she had the shorthand below. So above shows each of the steps, and below's got the shorthand. Sorry, Carly, I wasn't even looking at your. She had already drawn all of that out for me nicely. So there's the longhand version of it, and here's the shorthand version of it. Jeez. So in this particular case, then we have this coming out to a proton, and that's the shorthand version of it. You can have these guys resonate out and then resonate back if you like. Yep, makes sense? Okay, so this is the very first priming step of glycolysis, as you recall. What's this molecule here, chat? Glucose, good. And this molecule here? Good. We'll have a quiz on that at the end of next week, so we'll be relearning all those structures. Very good, everybody. All right, shall we do a couple more examples? Do you want? Does everybody feel good with the carbonyl chemistry? Should I do an aldol cleavage or shift base, or one more of these? No votes. Another example? One more, Daria asked for, and then somebody else says shift base next. Okay, so let's do this guy. Okay, this is another good example of another additional elimination. Where's the one you have? That one there. Yeah, this one's kind of a weird one because normally we, yeah, that's fine. We'll do it. Actually, I don't want to do that one as our first example. Let's do this guy here. I like this one better. It's more kind of a more normal one. So we have, in this particular case, we have this molecule coming over to make this molecule here. This is phosphoglycerate mutase, which is an enzyme that takes a phosphate off and puts a phosphate on in another position. So it's a part of the glycolysis, as you probably recall. So what's the nucleophile here in this 3-phosphoglycerate molecule? Where's the nucleophile, chat? Hydroxyl, that's right. And so this guy got a lone pair of electrons. What's the electrophile? Correct. Electrophile is what? Yes, the phosphorus. Absolutely right. So the shorthand version of that, as I would draw it, is just like this. You end up with these two molecules. Does everybody feel comfortable with that? Is that obvious? Yep. Good. So if you're starting to see a pattern here, effectively all of the molecules that we're going to work with are going to look just like this. Okay. Now I want everybody to do one on their own. Let's see. I guess I'll do one more example here. Let's see. Oh, this is a great one. What's the nucleophile here for this reaction on ornithine? Chat. Amine. That's right. Which amine? This guy. Right? Not the amine, this guy right here. So, and what's the electrophile? Electrophile from the chat. Carbonyl, that's right. And this is a really common molecule to start reactions called carbonyl phosphate. We'll see it several times. It's one of the first things used in starting nucleotide biosynthesis. It's used for a lot of things, but it's a priming molecule. So this is the addition here, and then that goes, if we want to go through intermediate, it's going to go like this through the intermediate form. And then you go like that, and you have the loss of a phosphate, and you end up with PI and citrulline. This is first step in urea cycle, part of the urea cycle, one of the pathways we'll learn about. Does everybody see how, do you have a reversible reaction arrows for this reaction step? Yeah, these are definitely reversible. All the reactions are in, most of the reactions that don't involve the loss of ATP are reversible. And many of them will go back and forth, and what drives them forward or backwards is the concentrations of products and reactants. So if you had lots and lots of citrulline, lots of phosphate, this would go backwards, although there's a big negative delta G going in this direction. So this is the happy direction to move, but you can move things backwards by having lots of by changing the concentrations of products, right? Let's see. See other examples here. What should we do? Should we do a shift base? Shift base or an aldol cleavage? Let's see, which one have we got here? That's a sulfur. Oh, this is a good one. Let's do aldol cleavage. So. This is actually kind of a hard one to start, but it's biologically relevant, so why not? We can work through it. This reaction is part of glycolysis. It's called aldolase. Chat, why do you think it's called aldolase? We hear somebody talking in the background, but no explanation of why it's called aldolase. It's called aldolase because it uses an aldol cleavage reaction. So we'll see a recurring theme here. We go through glycolysis, and why I want to work with you on this is basically every reaction in glycolysis is either SN2, additional elimination from carbonyl, or aldol cleavage. So after you learn this, I can give you all the structures of glycolysis in the TCA cycle, and you can actually get together and predict the reactions from scratch. And so we're going to do that next week. But here's a good preview. So before you can do anything with the sugar, you kind of have to open it up. So I think you guys already learned this reaction in organic chemistry. It's just a ring opening reaction. So the way this one works here is you have a base that abstracts a proton. And so the first step is just to open up the ring. This guy goes to a proton here. And then you end up with this structure, right? So this bond, let me see if I can get a green pen to highlight it here. This bond right here ends up being this guy right here. Does that make sense? Everybody to chat. Here. What is this one called? Oh, this one here. Glyceraldehyde phosphate. Are those familiar? You guys remember that? Yes. This is all from intermediates from glycolysis, right? So the way this works is a base abstracts this proton, okay? And these guys have to go to here. And why don't we just get a double bond here? Answer? Chat? And just leave it at that. Texas carbon. Brandon, you're right. No Texas carbons allowed. So we can't have 5 bonds to carbon. This carbon's got to kick something off. Where does it go? Where does it go? Did you notice this guy is alpha, beta? This guy's beta to carbonyl, isn't it? That means those electrons have somewhere to go. These guys do. They can go here. Why can they go there? Chat? Because resonance, number 3, remember? So that's exactly what they do, and you end up with this intermediate form where this guy resonates out to a proton. And that proton here, I'll just highlight it in green so you can follow along. So this bond here that we just made ended up being this bond right here. We got the terminal phosphate. This guy right there. Yeah? Yeah. And then we ended up with this glyceraldehyde and this structure right here. So this hydroxyl here ends up being that ketone, or that that oxygen ends up being in the aldehyde. Make sense? So then how do we move along? How do we get from this weird intermediate right here to dihap? Well, the way we do that is a base abstracts the proton again, just like so. That guy resonates to there. That guy picks up a proton. And you end up with dihap. Does that make sense, everyone? Aldolase. Cool, huh? So, should I do another aldol cleavage reaction? Yes, yes. Let's do a simpler example now. I think I have one already loaded from a while ago. Let's do this guy. This guy is a good one. From last year. So this is just going to be a general kind of guy. Let me clear it up so that's not so ugly. So in this case here, we've got the hydroxyl carbon here. Looks like that. Okay, and so the aldol cleavage reactions always start by abstracting abstracting a proton and breakage of a bond beta to carbonyl. So everybody in the chat, where's the beta to carbonyl bond? It's this guy right here. Where's the carbonyl? Here's the carbonyl, right? So this guy's alpha, that guy's alpha, that means beta. So that's got to be the guy that's going to break, right? So how do we get there? Well, in order to break that bond, we abstract a proton, right? When we abstract that proton, the electrons resonate down to there, and they start to form a double bond, but they can't form a double bond without kicking something out, because why? Texas carbon, good, thank you. No Texas carbon, and so in order for this bond to form, this has to move, right? And this would form a Texas carbon on the carbonyl if it weren't for the fact that the carbonyl can resonate out. Does that make sense? So that takes you very conveniently to this molecule right here. I'll draw it in the same orientation that we have on the slide so that it makes some sense. So we have a hydroxyl here, and then we have our double bond formed here. So this is just drawn in the same orientation as the slide deck. We can put our CH2 there, right? And then we'll have our aldehyde and our CH3 group on the end. Does that example make sense to people? Yep. Yep.
Yeah. Ahorita no tengo hambre.
All right, so shift base. Does this require shift base as well? No, the answer is no. But shift base and all these carbonyl chemistries, they have a theme that is repeating here, which is we have these reactions happening on the carbonyl. Let's do a shift base reaction. I think for that, I'm going to go back to our main slide deck. And so, whoops. I've got to go to the right slide deck, that one there. So we had just showed you the aldolase reaction. So So the aldolase reaction doesn't require nitrogen, doesn't require Schiff base, and it'll happen all on its own, just out in water. But in order to control things and hold them down, so enzymes frequently do use a Schiff base intermediate to perform the same kinds of chemistry. Also, the thing that they can do is Schiff bases can act as a pseudo-carbonyl to allow you to get around this beta to carbonyl bond breakage issue. It can provide a kind of pseudo-carbonyl to break other kinds of bonds. But let's just go through a simple reaction here where we do a Schiff base. So what is Schiff base? Schiff base is this functional group right there. That's all it is. Okay? It's that nitrogen double bonded to a carbon there. And it's something that originated from this guy here. Okay? That's all a Schiff base is. You're converting a carbonyl into this double bonded nitrogen structure. The cool thing about the double bonded nitrogen structure is that it can exist in multiple forms, and that makes it convenient for doing chemistry. So let's show you how this works. So, in this particular context, we have, we've got, well, first off, in order to get here, we have to open the ring. So how do we get from here to here? Somebody remind me quickly in the chat. Which proton needs to be abstracted? Ring opening reaction. Yes. This is actually C2. This is carbon 1, carbon 2, carbon. So this is carbon 2. So you abstract that proton, that resonates to there, this goes out to there, same reaction that we saw just a second ago. That's the ring opening reaction. You get this open chain form that you can actually do something with. Well, in this case, a free amine, and this is frequently a lysine on an amino acid, can attack the carbonyl, and when it does, you get this cool intermediate right here. See this? And the nice thing about that, now before anybody asks where did the other proton go, I just got to remind you, the other proton I don't need to account for. Why? For rule number 1. What was rule number 1? Yeah, exactly. Acid-base reactions are fast, so you don't need to bother with accounting for it. I'm not going to track it. It's not necessary. So we get to this intermediate right here, and then the cool thing that's different between this and other kinds of nucleophiles is, look, it can undergo a second step here, and this water can go away. Isn't that neat? So you're starting off from carbonyl, and you end up with this double bonded structure, and you've lost to water. Well, that's really interesting because now we have something that's just like a carbonyl right here. That's alpha, beta, away from a bond that can be broken, right? So you have something that's just like that Schiff base reaction where this happens and then this bond breaks, right? And where do those electrons go? They go right here. And how do they do that? It's because they can resonate back onto the nitrogen. And then you end up with this nitrogen here ending up right here. Is that cool? So that's how enzymes grab onto structures frequently and hold them around. And we're going to see a little later that they also use that to do some trickery to allow you to break bonds that are not beta to carbonyl by forming this sort of pseudo-carbonyl. We'll see that in the next lecture. Anyway, so that gets you back to here. Well, that's obnoxious if it's a permanent structure. So the cool thing about Schiff base is then they can go ahead and be regenerated. This is so neat. Love this part of it, which is that you end up getting back to the same structure that we had a minute ago. What's this called? That's called the Schiff base, right? Neato indeed, I agree. The stoichiometer is high for me on these reactions. I think it's super cool. And then a proton can be abstracted, right? And then when the proton is not abstracted, you can add a proton there, and then you end up with this intermediate here that we're going through. And then if you want to get the amine to leave from this group, then what happens? What would you do to reform the carbonyl? Chat? I can give you options. Let's give you options here. So I need to take away proton 1, 2, 3. All right, vote 1, 2, or 3. Everybody is right. Okay, so then the base subtracts the proton. Whee! And then something has to leave. Why? Why does something have to leave? So those can go away to a proton, and you end up with regenerating the lysine and getting your reactant. Isn't that cool? Yay! The enzyme has acted as an enzyme. So we're out of time here for today's chat. We're out of at our 50-minute limit. I will post videos like this. I'm here 3 days a week. We don't have any particular content, so if you guys want to see something else, you want to see more examples, that's the first time I ever saw Texas Carbon. I think technically that's not its real name. If you guys have other content that you want, make sure that you get in touch with email Carly, your lead TA, and I'll make sure to get it into our next week's live stream. All right, so guys, thanks. It's been fun, and I'm looking forward to our next live stream. Thank you, guys. Thank you, it was fun. Zoom. Okay. All right, and